Good morning, everyone. Today is the session 5 from the chapter of work, power, and energy, and the topic is conservation of mechanical energy. I have written the definition of the principle of conservation of total mechanical energy. The principle of conservation of total mechanical energy states that the total mechanical energy of a system is conserved if the forces which are doing work on it are conservative in nature. Now, what are the conservative forces? What is the definition of the conservative forces? I have written here. The conservative forces are those forces in which the work done depends only on the initial and the final position only. The gravitation force, the spring force are some of the examples of the conservative forces. Now, in order to make this discussion more understandable, I have considered here an example in which I am dropping a ball of mass m from a tower of height h. This is a tower. The height of this tower is capital H, and I will be dropping a ball of mass m from this point A, which is the top of the tower. So, as per the principle of conservation of the total mechanical energy, the total mechanical energy of a system is conserved if the forces acting on it are conservative in nature. So here I have written down 3 points. First, this one and this one. So what I have done is I have calculated the total mechanical energy of this ball at 3 different positions. That is on the top of the tower, at a point B, which is somewhere between the topmost position and the bottom most position of this tower. So this is at a height small h from the ground, from the surface, and this is the bottommost point of this tower. So when a ball at this point, that is at the point A, the velocity of the ball is 0. So the total mechanical energy of the ball will be equal to will be equal to the potential energy of this ball. So the potential energy of this ball at this point A will be equal to mgh, where h is the height of this tower. Here the velocity of the ball is 0, so therefore the kinetic energy will be equal to 0. So when this ball comes down to this point B, then let us say this point B is at a height h, small h, from the ground. So at this point B, the ball will gain some velocity. At the velocity here, I have taken it as VB. So at this point, the ball will have the total mechanical energy in the ball will be the sum of the potential energy plus the kinetic energy. So the potential energy is equal to mgh, where h is the height of this ball from the ground or from the surface, and half mvb square is the kinetic energy. So this is the total mechanical energy of this ball at the point B. Now when it comes down on the ground, so at this point the total mechanical energy of the ball will be equal to half mvc square, where vc is the velocity of the ball when it touches the ground. Okay, so at this point C, the potential energy of the ball will be equal to 0. So now these are the 3 relations which I have got in this example. So now we will be using these 3 relations in order to find the value of the velocity of the ball at this point B and the velocity of the ball at the point C. Since the total mechanical energy is conserved, therefore what I can do is I will be equating that since the total mechanical energy is conserved, Since the total mechanical energy is conserved, therefore, the total mechanical energy at A, that is EA, will be equal to the total mechanical energy at the point C. Okay. So, the total mechanical energy at the point A is equal to mgh, and the total mechanical energy at the point C is equal to half mv vc square. So here this m will get cancelled out. So it implies that the velocity of the ball, that is vc, will be equal to, that is vc square, that is vc square will be equal to 2gh, or it implies that vc will be equal to under root of 2gh. Okay, so this is the velocity of this ball when it touches the ground by the law of conservation of mechanical energy. So I have got the value of Vc, which is equal to under root 2gh. Now we will calculate the value of the velocity of the ball when it is at the point B. So, since the mechanical energy is conserved, therefore we can say that E A, that is the total energy at the point A, will be equal to the total mechanical energy at the point B. Now I will be equating it. So mgh will be equal to mg small h plus half mvb square. Okay, so here this m will get cancelled out. So what I will be getting here is gh is equal to gh, that is, this is a capital H, and capital H is the height of the tower, and this small h is the height of this ball from the ground when it is at the point B. So gh plus half vb square. So we can, it implies that half vb square is equal to, this gh will go on the other side of this equation, so I will be getting as g h capital H minus h. Or we can say that it implies that vb, that is the velocity of the ball at the point B, will be given by, this is this vb square will be equal to 2g capital H minus h. Okay, so we can say that the velocity of the ball, that is vb, the velocity of the ball at this point B will be equal to under root 2g h minus h. Okay, so the velocity of the ball at this point B is equal to under root of 2g in bracket capital H minus h. So I will be writing it here as vb is equal to h minus h. Okay, so this is the second equation which I have got. Now, since the total mechanical energy of a system is conserved, therefore we can also write that the EB, that is the total energy at B, should be equal to the total energy at C. Okay, so we can write that mgh plus half m vb square is equal to half m vc square. So from here m will get cancelled out. So we will be getting one more relation, that is gh is equal to, I will be taking this half vb square on the other side of this equation, that is we will be getting half vc square minus vb square, or it implies that vc square minus vb square is equal to 2gh. Is equal to 2gh. Okay, so this is another relation which I have got, that is vc square minus vb square is equal to 2gh. So this is the third relation which I have got by using the principle of conservation of total mechanical energy. So these are the three equations which we were able to derive using the principle of conservation of total mechanical energy. That is, if a ball is dropped from the top of a tower, then when it reaches the bottommost point, then its velocity is equal to under root of 2gh, where h is the height of the tower. And if the velocity of the ball anywhere between the topmost point and the bottommost point will be given by under root of 2gh minus h, where h, small h, is the height of that object, or in this case it is a ball, from the surface of the ground. So, and the third equation is that vc square minus vb square is equal to 2gh. So thank you very much for joining this session, and in the